Wow, RDL, wow. Wow. You know what? Even master students deserve positive reinforcement. Look at that. Look at that. Only there's always the undergrads that get positive, supportive compliments. There you go, RDL. Hi Vixen, how are you doing? Oh. There you go. In case you needed it. There you go. Hey, Smash Time, how's it going? Okay. So, boring math professor ate a rookie cookie and began to move horizontally and vertically. Wow. Just wow. Hey, the late one. 314. Okay. Smash Time. I'm glad your project is going well there. As moderator, you are in charge of that particular project. I'm not sure how to describe it, but it's very important work you're doing. So thank you. Right. You're handing out cookies to the class. Good. As they enter. Yes, all three of them. Yeah, good. Yeah. Oh, nice. Hey, Hangs, mate. How's it going? All right. Is that a special kind of cookie? Why is he laughing uncontrollably? What is this? Oh, wow. Wow, incredible. Wait, did you write all of these? Smash Time? What the heck is this? This is just so stupid. Okay. This is so stupid. This is completely dumb. I mean, it's wonderful. That's what makes it wonderful. Oh, what? Okay. All right, let's start the. Oh, this is not the right screen. Wait, what? Dude, my air server keeps acting up. It shows the last screen all the time. It's frozen. My bad. Hold on. Second class. Okay. Good. Yes, moving. Man, air server's been acting up. Swear. All right, everyone, let's get back in. Sorry about that interruption last week. All right, let's start where we left off. Okay, I want to say three things. When you have a finite extension of fields, which for now are subfields of C, today we will see a small detail where that assumption matters. If L over K is a finite extension of such fields, how big is this set that I told you to think about last time? The set of K-Embeddings of L into C. All right? That'll be the main theorem of that's the main theorem of chapter 11. And then I'll discuss some consequences of that theorem. In fact, when we put all the pieces together, including a statement from a long time ago, which I called "How big is the fixed field?" we will get the Galwa correspondence on like Wednesday. I'll go through that whole thing. So by Wednesday, we'll have the Galwa correspondence, fundamental theorem of Galois theory, for subfields of C. Really, it's for characteristic zero fields. All right. So, just a second. Something fell. All right. Okay, let's begin. I want to talk about three things today. And then we haven't done enough examples explicit. I want to discuss cubic extensions. Quadratic extensions are silly, especially in characteristic zero. So, because they're just adjoining a square root of an element. Structure is very simple. You know how to write every element. It's just boring. What about cubic extensions? Can we do some kind of in-depth study of those? That's what I want to do between now and Wednesday. Between chapter 11 and chapter 12. Okay, let's begin. Remember the situation we had. Have you read chapter 11? Yeah. It's chapter 11 is very important. Absolutely, RDL. Yes, it is. It is. However, the first part of chapter 11 is just extension lemmas that we've been emphasizing throughout. They're just the extension type lemmas. So that's the real ingredient of chapter 11, extension lemmas. And then from that you deduce like different characterizations of normality. Okay. So, let's begin. So let's consider the following situation. Okay. So now, I've encouraged you to think about the following set. The book doesn't do this explicitly, but it is implicit in there, and other expositions of the subject will emphasize this. It's worth emphasizing. Fancy E of L over K. It's the set of K-Embeddings. And I've decided to put C over here as the target field. Really, you can put, since L over K is finite, you can put Q bar, the algebraic closure of Q. Or K bar, really. K bar, the algebraic closure of K, if you'd like. Okay? But all the K embeddings of L into C, the ways that L manifests inside of C as an extension of K. That's what you think of, how you think of this. By the way, in case you were wondering, this is the same set as the set of K-embeddings where N is the normal closure of L over K. That's because, why is this? I'll just say the reason. Because if alpha is in L, then tau of alpha satisfies the same minimal polynomial as alpha. Okay, that's why every time L visits C, it will go into the normal closure. It'll be in the normal closure. The image will be in the normal closure. Normality is an inclusivity property. It's kind of a self-containment type property. All right? So, the fundamental result of chapter 11 is to establish the size of this set. Such an elegant answer. There are exactly degree of L over K elements in here, in this set. That's how many ways there are of presenting L as an extension of K. It's actually equal to the degree of this extension. Relates two seemingly different things perfectly, all right? There's a perfect equality of these two things. And now I'm going to put right in front of you, this will require separability. All right, and we'll see where. K-embeddings means the image contains K. No. K-embedding means that the map tau is identity on K, not just that it contains K. Yes, exactly. Yes, second sentence. I didn't read the first. Exactly. Tau restricts to the identity. So K, the prefix K dash will mean restricting to identity. Okay? Good. Awesome. All right. Wonderful. Because this is the main theorem. And the proof of this theorem goes by induction. So I'm going to just try to sketch the proof. But I'll present all the important ingredients. Okay. So let n equal this extension. All right? And then you go by induction. N equals 1 is stupid. Because then L equals K. And then you have only the identity map. Okay, N is so stupid. Okay. Yes, exactly. Exactly. Okay? So, man, this Kummer surface is ugly. Someone make the Kummer surface a little bit better. Okay. Next. So now what you do is you choose a primitive extension. This is a classic style of argument. So now, next. Choose any alpha in L, but choose it so it's not in K. So that we get this diagram. Okay, so K alpha is primitive extension generated by alpha, and then you got the rest. Okay, so I will let this extension have degree, just choose some S and T. These are the extension degrees. All right. Now, by induction, inductive hypothesis, we know that there are exactly S. So S times T equals N by the Tower law, and S and T are not. Okay, yeah. Okay, so by induction, a hypothesis, we know that there are exactly S different K alpha embeddings of L into C. K alpha now, procrastinatation. So, embeddings of the big field that keep K alpha fixed. Think of like a little flower where you've got L, versions of L, kind of rotating around this K alpha. That's kind of the mental picture you want to think of this embedding set. Okay, so there are S different ways of embedding L into C that fix K alpha. We can give them names. F1 up to Fs. All right, they fix K alpha. All right. So that's the inductive step. Next. So this is the first thing. Second thing. Okay. Yes, it's a strong induction. Exactly. Whatever the words are for those different kinds of induction. Okay, so next. Recall that if alpha 1 and alpha 2 share the same minimal polynomial, then there exists automorphism, a K-automorphism of the normal closure of L. I'll call it tau, such that tau of alpha 1 equals alpha 2. This is because of facts from chapter 9, I think, that you can extend any K homomorphism to the level of splitting fields, where the K homomorphism will upgrade to an isomorphism on splitting fields. I called this the intrinsic nature of a splitting field. And normal just means splitting field. Sometimes it's better to think in terms of that version rather than not disturbing packets, as procrastination likes to think. Okay? So you can... in other words, the automorphisms, K-automorphism group of a normal extension acts transitively on elements in a packet. Okay? And so we apply that to the packet that alpha belongs to. All right, so we're going to do this. So in other words, so if this denotes the set of roots of alpha's minimal polynomial, the first one is alpha. I just wrote alpha for alpha 1. Alpha 2 is another one. Next one. Then we deduce the existence of what's it called? We deduce the existence of t different automorphisms, K automorphisms. Let's call them tau1. No. I'll call them G's to be in line with this notation. We deduce the existence of G different automorphisms which have the following effect. Gi of alpha is alpha I. Okay, just send alpha to any one of the partner elements, including itself. For example, you can take the identity for something that takes alpha back to itself. Identity automorphism of the field. Okay, N is the normal closure of L, by the way. Normal closure of L over K. All right, so we've got two sets of things now. One of them we know are embeddings that fix K alpha and send L into C. All right, therefore send L into N, actually. All right, so this... can replace this with N for the same reason as before. And then we have these things, which are automorphisms of N. And so now what you do is you create S times T functions from L into C. Now, write down probably S times T functions. These are homomorphisms because they're compositions of homomorphisms. Phi of ij. You do, for example, you can do, it doesn't matter which way, oh no, it does, okay. So f of j composed with g of I, g sub I. J is from S, I is to T. All right, these go from L into N and then back to N. So these are just, so GIs are automorphisms of N fixing K, and Ls are K alpha, and FJs are K alpha homomorphisms. All right? Now these things, these are elements of script embeddings of L over K. That's clear by definitions, right? Fj fixes K alpha, in particular fixes K. So there you go. And GIs fix K. So the composition fixes K. All right. Now, why are they distinct? Okay, why are these distinct? Okay, so what you look at is the effect that each one has on, first look at the effect that each one has on alpha. Well, what is it? It's, this is, f of alpha is alpha for all the f's. Right? Let me write it out in case you're confused. This is by design. Yeah? And GI of alpha is alpha I. Oh, I forgot to emphasize something. Sorry. I forgot, bad teacher. Look, the fact that I put T here for the set of roots, the number of roots being exactly equal to the degree, that's separability. When we say that a minimal polynomial of degree t has t distinct roots, separability. That's small little detail, but that's all that you need in order to generalize this subfields of C part of Galois theory to a much larger class of abstract field extension mathematics, okay? So the fact that I wrote a subscript t there is separability, which is automatic in characteristic 0. Okay, so look what this is. This is alpha I. And so GI, so that this means that the I's have to match. So if then the I's match, i.e. Okay, so that tells you that the I's match. But then if the I's are matching, you can apply GI inverse to both sides because they're invertible, right? GI is an invertible thing. It's an automorphism of N. And then you get that the J's will have to match. So what I just did was I just showed you that there are S times T distinct K-embeddings of L in front of us. Now, conversely, we need to show that every conceivable K embedding of L into C is one of these. So the last thing is every embedding tau is of this form. But look, you have an embedding tau. Tell me what it does to alpha. Well, it has to send alpha to one of the alpha i's because tau is a K homomorphism. Okay? So then if you do GI inverse composed with tau, this is a K alpha homomorphism. Because it fixes alpha. And K, of course, because both of these fixed K and alpha goes to alpha now. And so it's by induction, it's exactly one of those F's. Is an F. And then you're done with the whole thing. All right, the size of the embedding set is S times T exactly, which of course by the Tower law is the degree of the extension N, as promised. All right? So the number of ways of witnessing L as an extension of K, where K is fixed, one field in C, the number of ways of witnessing it is the degree of L over K. Very beautiful statement. Very elegant. Okay? All right. Good. That's the main crucial theorem in chapter 11. All other things kind of follow from it. All right? And from it and understanding what normality means. Okay. So, consequences. One, the first consequence. How big is the Galois group? Fine print. When L over K is normal. And I'm going to put in parentheses here. And separable. Because that came into the argument right there at that last stage. Okay, how big is this group when you have a normal extension? Answer. This group is exactly as big as the field extension degree. All right, so let's go through that. Okay. Let me write it like this. Notice the okay, why? Because when you have a normal extension, every element of this embedding set is actually an automorphism of L. Is a K automorphism. That's what normality actually means. That's another characterization of normality. Okay? Awesome. Every element is an K automorphism of L. But, and now you just use the previous counting. How many K automorphisms of L are there? Well, that means that there's this many, but this is equal to that. Okay? That's a consequence. All right. Next, 2. Okay. So here's a second consequence. Suppose L over K is finite. And it has Galois group, finite normal extension. Then this is weird, but it's something that we didn't actually know before. Then K is the fixed field. No, L of L. That's stupid. Of L. Then K is the fixed field of L. All right? It's clear that K is, of course, contained. Hi, Pandemic. It's clear that K is contained in the fixed field of L. obviously, by definition. But is it equal to the fixed field? The answer is yes. Compare this, by the way. Always compare with that Q adjoin cube root of 2 type extension. It's just to see exactly why we need conditions, terms and conditions. Carry that example through forever. Okay, then K is this. All right? Okay, why is that the case? Well, we know. Okay, so why is this the case? Because we know this thing. Huh? Oh, thank you, snail mail quail trail. Okay, so we know that this thing is equal to the size of the Galois group. By the previous point. So we know that the degree of the extension L over K is this size. But by chapter 10 stuff, linear independence of field homomorphisms, Dedekind's lemma, that counting argument. By previous, we know that L, how big is the fixed field? This is the size of G as well. Size of the group that's acting. Any group that's acting on L, you look at its fixed field, how far is that? It's the size of the group. Okay, and now you compare. This is equal to this, and so this extension is equal, this degree is equal to this degree. But that forces Tower law. Why is this going to be important? The Galois correspondence tells you a perfect dictionary between subgroups of the Galois group and subfields of intermediate fields between two fields. And the rule is basically take fixed field. So this is like an important ingredient. It's telling you what the fixed field is in a particular situation. Snail mail quail trail. It's Monday, Wednesday, Fridays this time. It's an actual course. Snail mail quail trail. We'll be going for a month and a half. Hey Megalomorph, how's it going? All right, so cool. This is great. This is great. Okay, what more do I want to say? Okay, I think I'll let you. So class, I want you to read the remaining consequences. All right, I'm looking at it right now. It's 11.13, 11.14. Okay, it's again just a counting. It all comes down. These are all consequences of the structure of the embedding set. How many elements there are in this thing. That's the lesson of chapter 11. To understand this number of embeddings is a powerful piece of information. Because I want to talk now about particular specific math now, because we've been doing abstract things for too long. I want to switch gears. So on Wednesday we'll use everything we've learned so far, the abstract stuff, to set up the Galois correspondence, to earn the Galois correspondence. All right? And then we're just one hop step away from showing that certain numbers are inaccessible by radical expressions. All right? We'll have to do 1 week of group theory, not even a whole week, 2 lectures, and then we'll be back to that main thread. So here's an interlude. I want to talk about cubic extensions. So one thing to practice, or to get straight in your mind, is to classify extensions by their degree and see how much do I actually know about extensions of degree 2, extensions of degree 3, etc. Extensions of degree 2 are really, really simple things. So quadratic extensions are basically obtained by taking k and adjoining the square root of some element. This is because you can complete the square. Okay? If you have any minimal polynomial that's quadratic, you can shift the element around a little bit and without changing the field extension, and you can get an element whose minimal polynomial is of the form x squared minus c. Right? Adjoining a square root, minus k. Okay? So quadratic extensions, we kind of know exactly what they are. They're normal because if you adjoin square root of k, you adjoin the other one. Minus the square root of k immediately. Normal. They have Galois group z mod 2z. Everything lines up, everything's easy. So the next thing to do is to look at cubic polynomials, or primitive extensions of degree 3. So suppose alpha is an element such that this field extension is cubic. That just means it's it's got index, it's a degree 3. Exactly. You need characteristic other than 2 to complete the square. We're in subfields of C territory. Exactly right, megalomorph. That's where this becomes less obvious, but it's still true that the quadratic extensions are normal. You just have to choose. They just don't have as nice a uniform description. So, what about cubic extensions? So there are actually 2 situations. There are exactly 2 situations. One situation is that this extension is Galwa already. Oh, sorry. This extension is normal and separable. Normal plus separable just means Galwa. That's what Galwa means. But it's already normal. Now this one looks weird. We haven't seen an example of this yet. But what I'm about to develop... Not really. Okay, what I'm about to develop is a criteria by which you can come up with these kinds of examples. Adjoining just alpha is already normal. It's kind of weird, right? It means that when you adjoin alpha, the other 2 roots were now like rational expressions involving alpha and k's. Kind of a puzzle. Or B, there's 2 situations. It's not normal, and therefore its normal closure is a degree 6 extension of k. What is the normal closure? You just take the splitting field. You got to adjoin all the roots. Explicitly, n is k adjoin alpha 1, alpha 2, alpha 3. all the roots, where I'm just always assuming I write alpha equals alpha 1. All right, the other two too. By the way, notice, by the way, that this is also just k adjoin alpha 1 and alpha 2 only. Because if I give you 2 of the roots, the third one can be deduced from the other 2. So how does this work? The sum of the roots is the sort of second coefficient in any polynomial. So if you have a polynomial, and this thing here, up to sign, is the sum of the roots. So when you adjoin all 3, it's the same as adjoining only 2 of them, because the third can be reconstructed in a field theoretic way. How do we know it's degree 6 and not, say, degree 9? Beautiful question. By the Tower law. So here we go. Let's answer that question. Man, I really like procrastination. They ask me good questions. They ask questions, period. Okay, so let's use the Tower law. Now this is k adjoin alpha 2. Exactly what Megalomorph is saying. Look, ask, what does alpha 2 obey over k alpha? This satisfies a polynomial of degree less than or equal to 2 over k alpha. Namely, you take alpha's minimal polynomial divided by x minus alpha. Does this make sense? And so this extension has degree less than or equal to 2. You just get this inequality in general. It's equal to 1 precisely when k adjoin alpha was normal already. It's equal to 2 otherwise. This guy is in k alpha adjoin t by the division algorithm. Procrastination. That's right. You see, because alpha is a root of m of t. So then you do division algorithm like this. Yeah, and you'll get something with alphas at worst. Fantastic. Okay, so this is instructive digression here. So if it's a 1, then we weren't talking about situation B. So it's got to be a 2. So in other words, the normal closure is 6 away from K. So those cubic extensions have this one or the other situation. All right? I'm now going to tell you another 1 or 0 situation. Okay, 1 or 0 situation. Exactly, Megalomorph. Exactly. 100% procrastination. Exactly. There's this basic bound on the size of a normal closure of a primitive extension. 100%. Yes. N factorial is as big as a normal closure can get. It doesn't have to be that, though. And this is a first case where you see this distinction. I'm going to have to go overtime, class. Please forgive me, but I do want to finish this example. It's absolutely gorgeous. It's fun to think about. Okay. So here's another dichotomy. Recall the discriminant. The discriminant Let me move this down. Wait, what is this? That was not drag. Let me move it down. Let me recall the discriminant for a second. Okay, let's write m of x as the cubic polynomial. Irreducible cubic polynomial satisfied by alpha. Okay? So alpha 1, alpha 2, alpha 3. Yeah, much better procrastination, much better n factorial. Okay, alpha 1, alpha 2, alpha 3 will denote the three roots, where alpha is one of them. Say the first one. These are the roots. Then the discriminant, okay, the little discriminant little delta was the product of differences, only one. You don't take the difference two different ways. Okay, so you go like this. Alpha 1 minus alpha 2, alpha 1 minus alpha 3, alpha 2 minus alpha 3. This expression, this number, it's a number. Okay? The true discriminant is the square of this. Now this capital delta is always in the original field. That's because capital delta is a symmetric expression in alpha 1, alpha 2, and alpha 3. No matter any permutation of those symbols, we'll keep this expression the same. And that means it is expressible in terms of the elementary symmetric expressions in alpha 1, alpha 2, and alpha 3. But those are basically, up to sign, the coefficients of this minimal polynomial, right? When you take roots and you add them all up, you get the second coefficient. When you take roots and you add up all pairs of products, you get the second coefficient, third, etc. You multiply them all together, you get the last coefficient. Yeah? Good. Or the constant coefficient. Great. So this thing will be a symmetric expression in the roots, and so will be in K. All right? Okay. So, here's the question. But this delta may or may not be in K. This delta, little delta, may or may not be in the ground field K. And so here's the dichotomy number 2. Delta is in K, or delta is not in K. By the way, if delta, little delta, is not in K, then it is a quadratic extension. It generates a quadratic extension over K. Because its square is in K. Okay? This ends up being the same as before? Exactly. This ends up being the same as before. Exactly correct. All right, so these two dichotomies are the same. How do you know whether you've got a normal extension or not? Okay, so you join the root of a cubic polynomial, you're either going to get a normal extension right away, or you're going to have to adjoin two roots to get a normal extension. And what's discriminating between those two situations is this little discriminant, whether it's in the ground field K or not. Okay, so how do you prove something like this? You use what we just learned about the size of Galois groups and fixed fields to the following situation. This is okay. Now suppose we're in situation 2. So let's suppose delta is not no, let's suppose delta is in K, but assume that we're in situation 2, that this is a degree 6 extension. We're going to arrive at a contradiction. I'm just trying to set up a contradiction. Okay, so what you look at is this field. Okay, sorry, I'm all over the place. The size of n over k is 6. What that means then is the Galois group must be the full symmetric group S3, because n over k is normal, and so its Galois group is the same size as the field extension by what we just learned. All right, so the size of the Galois group is 6, but the Galois group must be a permutation, elements in the Galois group must permute these alpha 1s up to alpha 3, and any element of the Galois group is determined by what it does to alpha 1 up to alpha 3, because n is the field generated by those three things. If you know what a field automorphism does to these three numbers, which have to go to each other, then you know what the field automorphism is. And so it's got to be the full symmetric group S3 rather than some subgroup of it. All right, so we know exactly what the Galois group of this extension is. All right. So now you look at the subgroup A3. The even permutations, the rotation of the equilateral triangle. Yeah? The subgroup generated by 1, 2, 3. And you take its fixed field. By what we just learned, we know everything about these things. This has to be a degree 3 extension, because the size of a fixed field is size of the group away. Let me know that 3. So that means this is a 2. Okay? But then this is a quadratic extension. And so the fixed field is k adjoin a square root of something. Let me write it like this. K adjoin beta, where beta squared is in K. All right? But wait, now hold on a second. Hold on a second. Now, consider beta divided by delta. Consider this element. And I want to act by the Galois group on this element. Chat. Okay. Act on it. If you take an even permutation, what happens to this element? Well, it's itself, because beta is a generator of this field extension, so it's an element in this fixed field under even permutations. And delta, little delta, is fixed by even permutations. That's how it's kind of created. All right. So this element is fixed under even permutations. Now, what if you take an odd permutation? An odd permutation will definitely change the sign of delta. Okay, just go play with delta, little delta. Okay. It also has to change the sign of beta. Because otherwise, beta would be fixed by the whole group. And it would be therefore contained inside of the fixed field under the whole group, which we just learned was K. We just learned that the fixed field was exactly K and nothing bigger. All right? And so, no matter what you do, beta over delta is fixed by and so the fixed field is K adjoint delta no matter what. Now, but if little delta is already in K, that means that this diagram is crazy. It means that this is gone, and all we have is a degree 3 extension of K. And so our original K adjoint alpha over K had to be normal already. N equals K adjoint alpha. And then the other situation is if not, and then you get not a normal extension. That's why knowing what happens to where little delta is discriminates between whether capital N was degree 6 extension away or a degree 3 extension away, being K alpha itself. Okay, and now I'll translate delta being in K as a slightly more easily checkable requirement. It's more easy to check whether the square, which is capital delta, whether this is a square right? That's the same thing as saying whether this square root is inside of K or not. All right. Why is this easier check? Because this is some beautiful of the cubic polynomial. Oh, see ya, Crush Face. Welcome and welcome. Thanks for being here. All right. So, how do you check whether a cubic, when you adjoin one root, you've adjoined them all, meaning normality? Or, how do you find a cubic extension whose Galois group is A3? That's case A. You try to find an irreducible polynomial whose delta is a perfect square. And you can do that. I gave you... Well, the thing is, it's hard to write the roots down. It's hard to write the roots down of a cubic polynomial. How do you do it without writing the roots down? Yeah. That's... Okay, if you can write the roots down and you know how to manipulate them like you understand them, okay, then you can try to just compute this thing. Because it's an expression using differences of roots. But the problem is that's usually hard to do using the cubic formula for the roots expression. So that's why it's better to try to write this thing. That's why you'll see capital delta being the thing that people check for. But what they're checking for is whether this expression is a perfect square in the ground field or not. Okay? Now, I had given an example a long time ago. I forget what it was. I don't know if people probably can't remember it. Let me go back to my notes. Actually, I won't know which notes I've got it. But I wrote down a particular... Let me just Google. Example of a cubic polynomial with Galwa group something. A3. Cubic polynomial with Galwa group A3. Let me see if this is... I thought it was a Wikipedia article that I find easy. Right, there's like a first example. Here's an example. The discriminant, which is this delta expression, turns out to be 81. This is irreducible. Oh, we're doing, this is irreducible over Q because of the rational roots test. You only have to check like 1 and -1 to see if those are roots, and none of them are roots. Okay? And so, for this polynomial, 1 and -1. That's all you gotta check. Okay, so this is irreducible over Q. And so the Galwa group, so then this extension is already normal. Kind of interesting. All right, so this is, and it might be the smallest, so to speak, the smallest example. Actually, I thought, oh, that doesn't make any sense. I wonder, is this the smallest example? Maybe it is. Smallest coefficients that work over Q. Or integer coefficient. All right, so this is an example of a cubic extension. Is that going to be on the homework? There's nothing to say here. I mean, it's not, there's no question. I mean, you could try to compute this. Okay, maybe I should say a word about that. How do you compute capital delta? Oh, prove prove whether it's the smallest. Actually, you probably can prove it, because if you know how to compute capital delta, then you'll be able to like case check. Fresh face returns. Yeah. So you can look. How to compute capital delta, and then I think you can see a way to say that this might be the smallest example, smallest coefficients. Integer coefficients. Okay. How to compute capital delta, in case someone is not clear on this. So we know that little delta was this expression, and then you're supposed to square it. I square it. Oh my god, it's some horrible mess. And it involves alpha i's. Hey, you square that. That's... Yes, learning balance, that's a formula. That's a formula for the discriminant for certain kinds of cubics. I want to say where you get that formula. Most people have memorized that, but where does it come from? All right. So here's what you do to find this expression. On the other hand, if these are the roots, now I'm going to write it like this, minus s1 x squared. If this is the minimal polynomial, right? Then you know what these SIs are in terms of the roots. Right? You know this. So we get this. So on the one hand, you have these things. Why do we like this? Because what you're given is this polynomial. So you know what these three numbers are. What you're trying to achieve is this expression. And you kind of FOIL it out, and you try to match, like, oh, maybe I'll cube S2, and then I'll compare it with the square of S3. And I'll try to match coefficients until I get the expressions lining up. Literally, you play with it. You try to write this expression as a polynomial expression in these symmetric expressions. And what you get is the whatever learning balance, I don't care. What you get is this thing, this formula. So what you get at the end of the day is that if you start with a polynomial like this, it's exactly this expression. Meaning this P is just S2 or negative S2 and no, the P is S2 and Q is negative S3. All right. So there are these formulas you can easily witness yourself. You don't have to trust them by just playing the game of expressing a symmetric expression in terms of the elementary symmetric expressions, right? And in the 1800s, the classical invariant theorists were very well versed at writing, changing from elementary symmetric expressions back and forth to arbitrary symmetric expressions. It was a art form that is now long lost. Right? And this is like one particular example of that kind of calculation. So most people nowadays just remember this formula, but it comes from just explicit algebra puzzle. All right, brushing up on my history. Yeah, I don't think. Yeah, I mean this history is close to my subject, so kind of. Yeah. All right, so this is at this stage you kind of know exactly what's going to happen to a cubic extension in terms of the kind of Galois theoretic or field theoretic or normal versus non-normal point of view. There's one number that discriminates between two situations, and that is the discriminant. All right, that went over time by a significant amount, but class, you can go really fast through this cubic example, and it's not deep or anything. Very simple, but it's good to have the next layer of the layer cake down. So you could ask, what about quartic extensions? Can you just tell me the exact trichotomy or whatever is the situation for quartic extensions? It gets much more complicated for quartic extensions, and we'll develop it in the next week or so, 2 weeks. Can you just give me a finite list of situations that you will land in? And it's possible. It is possible to give such a list. And we'll kind of develop that after we have the main Galwa correspondence. Yep. Like there will be like 3 or 4 different types. Oh, one can know exactly how many there are by looking at the transitive subgroups of S4. But exactly how can you tell which situation you're in? There are ways. There are simple ways. Okay, and then no such description kind of exists for a higher degree. All right, now I finish with the credits, of course. Let's look at who showed up today. Who showed up? Who showed up here? Let's see. Megalomorph. Hope you're having a good day. I know, Femvox, I noticed that. Wikipedia suggests calculating the determinant of the Sylvester matrix. Is that the same discriminant? Probably. Probably. Yeah. Up to a sign. Oh no, but the sign matters. Hold on. I thought that there might be equal up to a sign. Anyway, I have to think about it. Who is Vixen? Vixen's okay. Femvox is here, barely, just barely. Yeah, okay, that makes more sense. Thanks, mate. Vixen. Vixen. Hope your semester's going well. Okay. Hangs, mate. Hope you enjoyed that cookie. Smash time. Smash time. Doing the Lord's work. Making who knows what as a moderator. I'm not sure what he's doing at this point. I think he's just gone rogue. But it's fine. You just let him be, and he'll do. Yes, learning balance. There were cookies. There were cookies. Learning balance is here. Learning balance. The homework gatekeeper is here. Next, who's next? Procrastination is here. The asker of questions. Good questions, too. Important questions. All my students. Oh my god. I have been so overwhelmed by the sudden surge in everything. I've got things with my research going on, publication issues, not issues, but, and then 4 classes of completely different parts of my brain. So my students, I know I didn't assign homework last week. There will be homework this week, okay? I'm almost back on track. In fact, I'm gonna give it right after this. I have to use a planner now. Let me see. Did I write anything in my planner yet? I don't think I did. I'm not sure I'm going to use a planner, but I thought about it. Okay, there will be homework. Don't worry. Next. Who else was here? Megalomorph. I'm using Notability on the iPad plus Air Server. It's not free. Oh, no. Bad timing. Bad timing, Eric Charnesky. Bad timing. Horrible timing. Did you not see me writing down everyone's name? You know what that means. It means cash. It means cash money, learning balance. It means dopamine. Hey, Arbitrary is here. Wait. So, Arbitrary shows up right when Charnesky shows up. Does that mean that Arbitrary was over there the whole time? Instead of here? What happened? Okay, no. This is bad news. This is bad. Pay you double. 2 times 0, 0. All right. You want some music, huh? All right. Well, what's some? Okay, we'll play some recorder for Eric. Okay. Play. All right, we'll play some relaxing, soothing music. Relaxing music. Play some relaxing music. Ready? This is for all the followers too, who followed and I couldn't pay attention to you, like Crush Face, Hi Guy Studio, your boy Dionycus, Chess, and Snail Mail. Hot cross buns. No. We'll do something else. We'll do Wow, insane, insane. I hope that was calming. And okay, now I gotta go. I have to. What's next? What was next? Commutative algebra, and then personnel meeting, and then intersection theory. Okay. Wow. What's going on here? What's going on here? Commutative algebra, primary decomposition. Yes, I am staying sane. I know these things. Yes. Okay. Fantastic. Everyone, thanks for showing up. My brain is about to explode. So here, these are the great people that make class so fun all the time. Right. That's what I'm teaching. Okay. All right. Do you guys want you? Okay, let's raid someone. Let's just raid someone. Who do you want to raid? Is there someone fast? Raid channel. Hey, Charneski, get back on. I'll raid you back. Just get back on. Get back on. Is there someone? Femvox, someone in the chat gives good suggestions for raids. Get on, Megalomorph. Get on right now. Just get on. Just don't put any screen on. Just raid you. You don't want it. Oh, God. I don't have any suggestions. Thank you. Thanks for that. Thank you. Thank you for that so much. Thank you. Raid Hikaru. Got it. Let's go. Ready? Go to Hikaru and tell him about discriminants. Is the discriminant a square or not? That determines normality. Wow. Incredible slogan.